Hi guys, so we are looking at the nucleophilic substitution of chloroethane. So this is an Sn2 reaction and this is regarding our haloalkanes, okay? So basically all we're doing is we're substituting one group on our haloalkane for something else. The haloalkane that we're interested in today is ethane chloride, okay, or chloroethane. It's this guy here. The base we're using, okay, and our nucleophile today is in our NaOH, and the product we're going to make is an alcohol, okay, so ethanol. So before we begin, okay, we obviously have to draw our structures, and as I've said in some previous videos, it's easier to draw your structures centered around the groups that we're interested in. So when I'm drawing our haloalkane, okay, so our chloroethane, I want to draw it so that the carbon to halogen bond is most obvious, okay? So the best way for me to do that is draw the carbon here. I know in an alkane I have a tetrahedral structure, so I have 4 bonds here, yeah? My chlorine is going to go here, and I write everything else around that. So I also know I have a CH3 group here. And again, when I'm drawing my carbon bond here, I'm drawing a carbon to carbon, isn't it? Because the carbon is bound to the carbon and this carbon is bound to the hydrogens here. So it's just a little thing to be aware of. And then this carbon is also bound to 2 hydrogens. So I have everything in my structure there for chloroethane. The next thing I have is NaOH. Okay, so this is an ionic structure. So we know it's Na plus OH minus. We're going to talk about that in a moment. So first thing I do is I look at the differences in electronegativity basically. So over on the structure here on my haloalkane, I know that my carbon to carbon bonds, there's no difference in electronegativity, there's nothing going to be happening there. I know there's no or not much difference between my carbons and my hydrogens, so again, they will all be staying put. I do know that there's a difference between my carbon and my halogen, which is chlorine here. I know my chlorine is more electronegative than my carbon, so therefore it's pulling electrons towards itself, and when it does that, it generates a slight partial charge and becomes partially negatively charged. Since carbon has had electrons pulled away from it, it now has a partial positive charge. Okay, so I know that my reaction is going to be centered around these guys. Now, so what about my NaOH? Okay, so we said there's an ionic bond here. When NaOH goes into solution, it will dissociate. Okay, so this dissociates. So it literally will split up into your Na plus and your OH minus. What we're really interested in, okay, and what is actually our nucleophile, if we recall our definition of our nucleophile, it usually is something with a partial or full negative charge, and it's usually the source of our electrons. And in this case, it's the oxygen here in this hydroxyl group. Okay, so again, when I'm showing these little dots here, these are the electrons that are in its outermost orbital, in its valence orbital, and these are the electrons that are available for bonding, and it makes this guy our nucleophile. So I want to draw that out so I actually know exactly just what I'm working with, okay? So I'm going to move that up for a moment, and what I really see then is my chloroethane staying exactly the same just for the moment. Still delta positive here, and still delta negative here. And what's really reacting is this hydroxyl group. That is my nucleophile. So I can pop that here just so you know. So Nu minus is how we can indicate the nucleophile. Now, remember, nothing is destroyed in this, okay? So it's your theory or your principle of conservation. So nothing is created or destroyed. It's still existing somewhere. So we're just going to pop our Na plus up here for the moment, just so we can remember him, because he will come in handy later on. Now, so with our Sn2 reaction, the first rule is our nucleophile, okay, which is attacking our carbon here, partially positively charged carbon, will always attack opposite the chlorine. Okay, so electrons are going to move and are going to attack opposite that chlorine. Okay, the bond between the oxygen and the carbon is forming, and the bond between our carbon and chlorine is breaking. And this makes chlorine our leaving group. Okay, so that's a new term for your glossary. Okay, for your own definitions. So it's our leaving group because it's leaving the structure, it's leaving the reaction. Okay, and what we get then is an intermediate or transition state, and we show this in our square brackets. And in this we have our carbon, and our carbon is now going to have 5 bonds. And we know our carbon isn't like that, okay? So we know carbons will always want to have 4 bonds. That's what makes it stable. So we know this isn't going to stay here for long. We know it is simply a transition state. So our chlorine's on this side, and our newly added hydroxyl group is on this side. Okay? Our carbon is still partially positive. Our chlorine is still partially negative, and so is our OH, okay? So none of that information has changed. So again, this is all happening at once, okay? So it's a concerted reaction. So it doesn't happen step by step, it happens all at once. And what we end up with is our product, okay? And our product is an alcohol. So we know our OH went on the opposite side, and we know those hydrogens didn't leave. So what we have here is ethanol, isn't it? So our longest carbon chain is 1 carbon, 2 carbons. So we know that's eth, and we know the functional group we have here is an alcohol, so it's ethanol. Okay, remember chlorine was just been kicked off there, but we did have our sodium, okay, your Na from earlier, and they'll go together. So we'll get NaCl as a byproduct. So it's just sodium chloride, and that becomes our byproduct. Okay, and that is an Sn2 reaction. So short and sweet. Few rules that you need to remember, and like that at the beginning of the reaction, just making sure that you know how to actually identify your electronegativity. So it's particularly important here, we can see, and our ability to identify your nucleophile here is very important. So yeah, so give it a go yourself and see how you get on. And there's a few questions on this in the problem sheet, so try them and see.